In the last few lectures, we completed common base configuration of transistor. In this lecture, I will explain common emitter configuration of transistor. In common emitter configuration, emitter is common to the input side and to the output side. This side is input side and this side is output side. We are using NPN transistor, and this junction here is collector base junction, and this junction is emitter base junction. We want to use this transistor as amplifier. We want to use the transistor as amplifier, and in order to amplify the input signal, the transistor must operate in active mode. The transistor must operate in active mode, and in active mode of operation, collector base junction is reverse biased and emitter base junction is forward biased. And in order to reverse bias the collector base junction, I will use the reverse biasing potential VCC. This is N type of material, so I will connect positive terminal to the N type material and negative terminal to the P type material, plus minus, and this reverse biasing potential is VCC. We have to forward bias the emitter base junction, so P type material is connected to the positive terminal and N type material is connected to the negative terminal, plus minus, and the forward biasing potential is VBB. We are using NPN transistor, so the base current is the entering current, IB is the entering current, emitter current IE is the leaving current, and like base current, collector current is also the entering current. We can also represent the common emitter configuration by using the symbol of transistor. I will quickly draw the symbol of transistor. We are using NPN transistor, so the arrow will be like this. Common emitter configuration, so emitter is common to the input and the output side. This is emitter terminal, this is collector terminal, and this is base terminal. In case of common emitter configuration, the input current is IB and the input voltage is VBE. The output current is IC and the output voltage is VCE. This is what we have in common emitter configuration. I will quickly write this down. The input current is IB, the input voltage is VBE, the output current is IC, and the output voltage is VCE. And we already know the emitter current IE is equal to IC plus IB, and the collector current IC is equal to alpha times IE plus ICBO. This is equation number 1 and this is equation number 2. These two relations are true for every transistor connections. Now I am interested to find out how output current varies as a function of input current. The output current is IC and the input current is IB, and I am interested to see how the output current IC varies as the function of input current IB. And for this I will use these two equations. We can write IC equal to alpha times inside the bracket IC plus IB, because IE is equal to IC plus IB plus ICBO. I will open the bracket and we have IC equal to alpha times IC plus alpha times IB plus ICBO, or we can write 1 minus alpha IC equal to alpha IB plus ICBO. I will divide both the sides by 1 minus alpha, and we will have IC equals to alpha 1 minus alpha IB plus 1 divided by 1 minus alpha ICBO. I have divided the left hand side and the right hand side by 1 minus alpha. Now this quantity alpha divided by 1 minus alpha is beta, and if beta plus 1 is there, this means we have alpha divided by 1 minus alpha plus 1. When you solve this, you will have 1 divided by 1 minus alpha. So 1 divided by 1 minus alpha is beta plus 1. This is beta plus 1. So I can write this equation as IC equal to beta times IB plus beta plus 1 ICBO. Now we will see how beta changes with change in alpha. Let's take the first case number 1. In this case, alpha is equal to 0.98. So beta is equal to 0.98 divided by 1 minus 0.98. When you solve this, you will have beta equal to 49. In case 2, alpha is equal to 0.95. So beta is equal to 0.95 divided by 1 minus 0.95, and this is equal to 19. You can see slight change in alpha changes beta significantly. Therefore, beta is very sensitive to variations in alpha. Alpha is the amplification factor in common base configuration, and it is less than 1. Alpha is less than 1. Beta is in orders of 100, and the range is from 50 to 400. This is the range of beta. Now we will move back to the equation, and I will try to simplify this. Beta plus 1 ICBO is represented as ICEO, the reverse saturation current in common emitter configuration. So we can write IC is equal to beta times IB plus ICEO. ICEO, the reverse saturation current or leakage current, is much smaller than beta times IB, so we can neglect this, and we have IC equal to beta times IB. This implies beta is equal to IC divided by IB. This is what we have. Beta is called the current amplification factor. Beta is current amplification factor, and it is equal to IC divided by IB, and we have already seen it is from 50 to 400. Let's say the input current, that is the base current, is equal to 1 milliamps. Beta, the current amplification factor, is equal to 100. Then we have to calculate IC, the output current. So IC is simply equal to beta times IB. So IC is equal to 100 milliamps. The input current was 1 milliamps and the output current is equal to 100 milliamps. So there is amplification of the input current, and generally transistors work as voltage amplifier, but the common emitter configuration work as the current amplifier. This is very important point. The common emitter configuration works as current amplifier. Generally transistors work as voltage amplifier because of transferred resistor, but common emitter configuration works as current amplifier. There is one more thing that I want to explain. I want to compare the reverse saturation current in common base configuration and in common emitter configuration. This is the note. In case of common base configuration, the output current IC is equal to alpha times IE, the input current, plus ICBO, whereas in case of common emitter configuration, the output current IC is equal to beta times IB, the input current, plus beta plus 1 ICBO. If we compare the two equations, we can see the leakage current is having more contribution in case of common emitter configuration, whereas leakage current is having very less contribution in case of common base configuration, because in this case ICBO is multiplied by beta plus 1. Beta plus 1 is a large quantity because beta is a large quantity, and we are multiplying it with ICBO, so the contribution of leakage current in the output current is more in case of common emitter configuration, and the contribution of leakage current to the output current is less in common base configuration. I think this is clear to you. Let's say beta is equal to 99, so we are multiplying ICBO by 100. I hope this point is clear to you. I will end this lecture here. See you in the next one.